Welcome to today's webinar, part of the AIChE CAST Division's Outstanding Young Researcher Award that we're recognizing today. We're honored to have Professor Zhang presenting toward explainable stochastic optimization for decision-making under uncertainty. Dr. Zhang is an associate professor in the Department of Chemical Engineering and Material Science at the University of Minnesota. He earned his bachelor's in mechanical engineering from RWTH Aachen University in 2011, followed by an MS in chemical engineering from Imperial College London in 2012, and a Ph.D. in chemical engineering from Carnegie Mellon University in 2016. Before joining the University of Minnesota, Dr. Zhang gained industrial experience at BASF in Germany and Houston. His research focuses on computational methods for decision-making in complex process systems with applications spanning sustainable energy, advanced manufacturing, supply chain engineering, and bioengineering. Dr. Zhang's contributions have been recognized with several honors, including the one we're recognizing him for today, which is the AIChE CAST Outstanding Young Researcher Award that was given last year, and the McKnight Land-Grant Professorship in 2023, and an NSF CAREER Award in 2021. So with that, we'll go ahead and turn it over to Professor Zhang for his presentation. Welcome.
Thanks, John, for the kind introduction, and thanks for the invite to present at the CAST webinar. I'm a big fan of the webinar series, usually watching them on YouTube, so it's been a great resource. So thank you for doing this and organizing these events. So what I'm going to talk about today is as a more recent research topic in our area, in our group, and we've been working on decision making under uncertainty for a while now, but this greater focus on explainability is a more recent focus of the group. Although this work was probably done in, I think, 2022, so this is already a couple of years ago. But I'm just presenting here again for the broader community. So we're talking about explainability, explainable optimization, and in particular, what I'm going to talk about is one piece of work that we've done in explainable stochastic optimization or stochastic programming, where we try to make models or develop systematic methods that make them more interpretable, more explainable to the user. I added a few slides at the beginning just to talk a little bit more broadly about explainable optimization. So really, the broad or the main question we're trying to answer is how we can explain complex optimization solutions to the user, and the user potentially being someone who's not an optimization expert, someone in the field using the tool, trying to get the optimal decisions to implement, but who needs to be able to rationalize these decisions and trust them so that they will actually implement them. Of course, this is not a new problem. Explainability has been a long-standing challenge in optimization applications, and usually in practice, what it takes to understand and interpret solutions for especially complex problems often requires both a subject matter expert who understands the domain, who understands the application, as well as an optimization expert who developed the model, who knows the intricacies of the optimization model, as well as the algorithms and so on. And often it's kind of considered an art for the optimization expert to, develop these models that solve quickly, and then also being able to debug them and kind of scrutinize them in order to find maybe what's wrong with the model, what's wrong with the solution. But that's often not something that a subject matter expert, who's just a domain expert in that application, can do. And what that often leads to in practice, unfortunately, is that advanced optimization tools are being implemented and deployed, but because there isn't always kind of the optimization expert sitting alongside the subject matter expert working or using that tool, at some point it gets abandoned because the user doesn't quite understand what the solution is, doesn't quite trust it. So then the user doesn't use it for a while, and then over time it just gets neglected and abandoned, and they don't use it anymore. Which is of course a problem in practice, where you invest a lot of resources to develop them, but then they don't get used properly. Again, this is not a new problem. People working in the industry, people working in the practice optimization, they know this very, very well, and they know how much time and effort it takes to really properly deploy these tools. But then in research, there has been this recent surge in interest in developing more systematic methods for explainable optimization. I would say the kind of explanations that we have nowadays, typically they are first of all kind of domain specific or specific to your application. The second, really requires this really interaction between the optimization expert and the domain expert to work on these. And so now there's the greater interest in developing more systematic methods for explainable optimization. And this is really inspired by this again, similar surge, maybe bigger surge in explainable artificial intelligence, explainable AI, where the problem is that you want to explain or better interpret the predictions from a machine learning model, where these machine learning model become more and more kind of black box type of models, for example, or really large neural networks, so that you put some inputs in, it spits out predictions, but then you don't quite know where they're coming from or why these predictions are made. And this has become increasingly important because these predictions are now driving on more and more decisions that are made. I think a typical example that's made in this that's brought up in this area is this application of offering loans, right, from a bank standpoint. So if you apply to take a loan from the bank and the bank rejects you, and then the question is, okay, why did they do that? So you have a certain, as a person, you have a certain credit history, you have certain features in a sense, and so the question is, what made them decide not to offer you that loan? And often increasingly there's a machine learning model behind it. And so the question is, okay, what did the machine learning model do? What could you have done differently to affect that decision? And these decisions are, of course, impactful in finance and healthcare and so on. Now, explainable optimization, there has been recent work on these more systematic explanation of explainable optimization methods. And explainable optimization is really mainly concerned with the outputs of an optimization model, which are, of course, optimal solutions, and of course concerned with the question of why a solution is optimal or is not optimal. And if you think about it, really, an optimization model typically for us is not a black box, right? We formulate the optimization model, we'll formulate the objective function, we'll formulate the constraints, and so we really know what's going on. But then what we have is not a direct functional relationship between the inputs and then the outputs. It has to take the model, it has to take the data, and then go through an optimization algorithm before it spits out the optimal solution. So from that sense, it's like a black box because we don't quite know what's going on in the optimization algorithm. I think it's often talked about, okay, we want to understand how the optimization algorithm makes these optimal decisions, but the way I see it is really about reasoning why a solution is optimal, right? It doesn't matter which algorithm you use to get to the optimal solution. What really you want to understand is, why is the solution optimal versus a different one? What could have been done differently to achieve a different solution, for example, right? So these kind of questions. So if you look at these systematic approaches, that the existing ones are very traditional ones, like sensitivity analysis, right? You open up any linear programming textbook, you will see a chapter on sensitivity analysis, which tells you, okay, how should you change certain parameters, let's say the right-hand side, that would affect the optimal value. So that gives you some local information in terms of, okay, how do certain parameters affect your optimal solution or the optimal objective function value? And of course, the other one is what we do over and over again in practice, which is what if analysis. If we want to understand our own model better, we change the parameters, run a scenario, get some insight how the solution changed, and then run a different one depending on what we saw. And that kind of what if analysis is what we typically do in practice, and also what typically is done in interacting with a domain expert or with a user who uses that optimization model. But then there are more recent approaches that are trying to go kind of a step further and trying to provide explanations that are presumably more kind of informative. And one big one is what's called counterfactual explanation. And this one really, is receiving a lot of attention because of its application in explainable AI. And there was a 2017 paper where they talk about how counterfactual explanations can be used to really satisfy the needs from this general data protection regulation from the European Union, which kind of requires you to provide explanations to machine learning models. And from that point on, there's been like tons of papers on counterfactual explanations, more in the context of explaining machine learning models. But now people also have adapted this for optimization models. So what is a counterfactual explanation? Counterfactual explanation, very easy, is say, okay, I see this is the optimal solution, but I, as a user, I would have implemented a different solution. Then I want to ask the question, okay, why is my solution not optimal? Or I can ask the question, how do the parameters need to change so that my solution is optimal? So then that will provide some information to me. It's like, okay, why is my not optimal compared to the one that's suggested by the optimization model? Right. So that information, how the parameters need to change so that another solution becomes optimal. That is a counterfactual explanation. And counterfactuals are like a big topic in cognitive science. So that's where it's coming from. The other kind of big area that's where there's been a lot of recent work is really creating surrogate models for your original optimization model that are more interpretable, essentially easier models that allows you to more directly see the relationships between parameters and optimal solutions. And often these are built like more locally. So saying, okay, I have an optimal solution, and I can't really build a surrogate model for the entire feasible space that it's more interpretable. But then let me build one that's locally around this optimal solution, and then that gives me maybe more interpretability or explainability for your solution. Of course, you can also just do it, say, okay, I have my original model. I take a lot of different inputs. I get a lot of different optimal solutions. Now I try to train like a decision tree on this, and then that decision tree is presumably more interpretable than my original optimization model. Kind of the downside of some of these methods is they may not always be that scalable, right? If you think about a very complex optimization problem that we encounter in industrial practice with thousands and thousands of constraints and variables, then having a decision tree for that high dimensional problem may not be practical. You may get a very large decision tree that in the end is also not as interpretable or explainable. The other thing that has been emerging is the use of large language models in this area, and it's not used to provide like a new method to explain things, but it's really providing an interface to interact with the user, which is really nice. Before you needed to be you needed to have that optimization expert who knows how to run the model, how to change certain parameters. So now maybe as a normal user, you could just ask verbally kind of your question, and then it would spit out kind of an explanation or answer to your question. So then if you want to do sensitivity analysis, what if analysis, or even counterfactual explanations, you can just ask one question. You can say, okay, run this scenario, what happens? And it returns that back to you. And then you want to run to the different one. So through that interaction, of course, you have then the chance to get better explanations for these models without having another optimization expert who actually does these things for you in the model. So that can be pretty powerful in this context. And there has been, for example, this OptiGuide application that Microsoft has put out to do this for supply chain optimization. Also, Professor Zhang Li at Purdue has this OptiChat that does similar things, including it also does feasibility diagnosis on your optimization model. Finally, I think the major challenges here are, I would say that at this point, there's no silver bullet to explainable optimization, which I think is understandable. There's no one method that works for everything, and then everyone would consider to be explainable or a good explanation. And also because what's considered a good explanation is very subjective. So what I consider, and also based on your knowledge, right? What I consider for a certain application to be a good explanation, or to be very easy for me to understand, may be difficult to understand for someone else, or vice versa. So in a way, I feel like really in this field is we'll probably end up with a portfolio of different creative solutions to this, and then based on your application, based on your needs, you can choose them, and maybe you can through the use of LLMs, you can then very easily query these different methods to better explain your model. So that's kind of my quick review or take on explainable optimization, this re-emerging field. If you look at all these different papers that we're citing, all of them are from the past 5 years. So it's really a kind of a emerging area in optimization that has received a lot of recent attention. And I believe moving forward, there's a lot more work to be done in this field. So now in the remainder of my talk, I just will talk about one piece of work that we've done contributing to this area. And here we focus on a specific type of problems, which is stochastic optimization or stochastic programming. That is used for decision-making under uncertainty, of course. I mean, I don't really need to motivate this to this audience, but just to have this introductory slide here where I say uncertainty is ubiquitous. And of course, uncertainty can have major impacts on what you do. And so here are just a few examples. Of course, the first two are really bigger impact scenarios, the supply chain disruptions here caused by what happened in the Panama Canal. Here was extreme weather events, for example, a few years ago in Texas, where you had brownouts and blackouts in your power grid. Oil and gas exploration, maybe where this is uncertainty of how much oil and gas you can actually get out of the ground once you actually develop that field. And then stock market, of course, the classic example where you don't know how prices will go in the future, but you need to make investment decisions in light of that uncertainty. So really, that says decision-making must take uncertainty into account. So how do you do it? How do you model it if you want to put it in an optimization problem? There are various way of doing it. Here I will focus on stochastic programming. So one popular way to do it. And what I'm showing here is a corresponding deterministic optimization problem where you have these X variables that this one I call them first stage decisions, but really in the context of decision, deterministic optimization doesn't make a difference whether I call them first stage or second stage, but it makes more sense once you go to the stochastic setting. And then, so this X here denotes the feasible set for X, this Y here, these are my second stage decisions. And then this calligraphic Y here is a set of feasible Y, given the X given the values for X and given the values for these X's, which are my model parameters. And then this is the total cost, where one part of the cost depends on X, and the other part of the cost depends on X, Y, and my model parameters. So for someone in process systems engineering, I think this is most commonly, interpreted as maybe a design problem, right? Where X are design decisions. So think about designing a chemical plant. So you need to make decisions in terms of what reactor, what distillation column, what flow sheet, how are they connected, and so on. So that's your design decision. But once your plant is built, you have to make operational decisions depending on your daily operating conditions, right? How your demand is, what the weather is, what the ambient temperature is, and so on. So then these will be your Ys. These will be your operational decisions. In this case, I call them second stage decisions. And they, of course, depend on Xi. Xi would be what I talked about in terms of, let's say, the demand that changes in your operation, or some other conditions that change in operation, or maybe degradation in your equipment units, and so on. Okay, and so then the total cost is a design cost plus an operating cost. And stochastic optimization, and this is we focus on two-stage stochastic optimization. So that's why, again, these two decision stages. What we do is that we assume that these model parameters that they are uncertain, or at least some of them are uncertain. For example, demand is uncertain. You cannot fully predict into the future what the demand will be. So then we treat them as random variables. Once you treat them as random variables, you need to think about, okay, how do I need to write my objective function now? So in this case, this is a common way to write it, is to write it as the expected outcome. So this is the expected total cost given that C is now a random variable. And then the other thing that's important is that now my Ys, the second stage decisions, they can be chosen after the realization of the uncertainty. So after I see my demand, I can then decide how to operate my plant. So so that gives rise to this two-stage sequential decision-making framework where you first need to make your design decisions before you know what the realization of that uncertainty is. And then once you've put that plant in the ground and you are actually running it, now you see what's happening with your uncertainty, how they're realized, and then you'll make your second stage decisions in my example, the operational decisions. So that's why I denote them Y here as a function of C, because it will change depending on the realization of your uncertainty. So that's how you can generally formulate this kind of two-stage stochastic optimization problem. And what you do but the main challenge is this expectation term here. The expectation is generally intractable to write this out. Unless for example, if I have a discrete distribution, then you can write it out. Or what's used in stochastic programming is that if it's not a discrete distribution, we approximate it with a discrete distribution, which essentially means you have your probability distribution. You can sample from that, and then these samples will be discrete scenarios that then you can use to approximate that expected cost function. So what we're doing here is now, let's say we sampled S scenarios, or this calligraphic S is my set of scenarios. So then I will have the set of scenarios. Then for each scenario, I have a specific realization of my uncertainty. So this C bar here now denotes like specific values for these model parameters. And I have one set of them for each scenario. And then I have a probability associated with each scenario S. And then finally, in my recourse decisions now, I have specific ones for each scenario. So now these Ys also have a S index. So essentially, now my Ys would be my Y given that my C takes this value from that scenario. So then you can formulate this way, which is often called the deterministic equivalent of this stochastic programming formulation. And this is very commonly used, at least in research. And there's a lot of research on stochastic programming. There are a bunch of books on this. But really, the challenge we're trying to address is that essentially why this is still not used that much in practice, especially in the chemical industry. In other industries, it may be a little bit different, but especially in our chemical or manufacturing industry, stochastic programming is not a very commonly used tool. All right, so this is the kind of mathematical introduction to this. Let me give you just present one example to give you a little bit more of a feel how stochastic programming works. Since this presentation is about explainable stochastic optimization, so let me also try to explain a little bit more to the maybe broader audience. I know some of them are experts in this area, so you will for sure know that this may be boring, but for others who don't deal with stochastic programming every day, this may be useful. So let me start with this very simple example where you have a supply chain, essentially a supply chain planning problem where you have 2 production plants and 3 customers with uncertain demands. So then what you need to decide is how much, and we assume that you need to decide how much to produce, let's say for the next day, before you see the actual demand. So that means you need to decide how much to produce first, then you see the demand, and then you can decide how to distribute how much you're producing. Or you may have to purchase, these are indicated by these red arrows here. So you may have to purchase additional product to meet the demand if you didn't actually produce enough, right? So the data for this is that it's plant A is a bit cheaper than plant B. And then this dashed line here is the procurement cost. That means if you have to purchase from third party, then it's a lot more expensive than if you produce yourself. So you try to avoid having to purchase from third party. And then we assume we have 4 different demand scenarios with different probabilities. It's actually not that important what these numbers are. But this kind of captures, this is what we call a scenario tree. This captures kind of this sequential decision-making process where I make production decisions at this point before demand realizes. Then the demand will realize. And then once it realizes, I can decide how to distribute what I produce or purchase additional product in each of these scenarios. And then And these are the 4 scenarios. So we'll have 3 customers, 3 different demands. So you can see they're different. Really what, okay, this is how it's formulated. So my first stage decisions are, the amounts that I produce at each plant, and second stage decisions are, transportation, by Y, and external purchase by Y bar. So what you see here is I'm minimizing really the total cost, which the first term is my production cost, I being the set of plants, and then the second part here is my how much the cost of purchase, and then the cost of transportation. And then these are the typical constraints saying, okay, I cannot produce more than my capacity. And this is really, I need to satisfy demand. So what I get to my customer needs to be greatly equal their demand. And then, but I cannot distribute more than I produce. So the very simple network constraints that I have here. Now, if you look at the deterministic solution, so let's first look at the deterministic solution, which just takes the expected demand, right? And the expected demand here will be for customer 1, 21.25, 24.25 for customer 2, 20.3.75 for customer 3. So then it decides to do this in terms of first stage decisions. The first stage decisions are producing 31.25, which is rounded up to 31.3. In units in Plan B, and 38 units in Plan A. So this is, of course, if you do the math here, the sum of them is exactly how much you need in this expected scenario. But then your actual scenario may differ from this, right? For example, in the first case, you actually the total demand actually exceeds the production capacity of these 2 different plants. So what happens then is that in this case, customer 3 cannot be fully supplied from these 2 plants. So then you have to buy 5.7 units from the market or from third party, which is, as we saw, is expensive. If you look at the 3 different other scenarios, so you can see actually the distribution kind of links here are the same in the first 3 scenarios. It differs in the last one. In scenario 2 and scenario 3, I'm producing actually more than I need. So then I don't need to purchase additional product. But then again, in scenario 4, I have to purchase additional product. Again, that makes it expensive. And so that's the key observation here is if you optimize for the expected scenario, you may not consider the cases where you actually don't produce enough to satisfy demand, and then you have to purchase additional product. Now, if you apply stochastic programming, which considers all these 4 different scenarios explicitly, then what it decides to do is, because it knows it will be expensive if I have to purchase additional product, it decides to produce more in these plans. So then it produces 37 here, 38 here. So now if you look at all the scenarios, I can satisfy all the demand, although there will be scenarios where I produce significantly more than I need. And then if you look at these, how these 2 perform, so what you see in each of these bars, this corresponds to that solution for the scenario. The light part here is your kind of first stage cost. The dark part here is the second stage cost. So you can see, especially in scenario 1 and 4, the deterministic solution does badly because it has to purchase additional product, whereas in the stochastic programming solution, which are the blue bars here, you do worse in scenario 2 and 3, but not that much worse, but you do much better in 1 and 4, which then leads to this what we'll call value stochastic solution of 6.2%, which is exactly this difference between these costs here. So this is an example of showing how stochastic programming works and how it can bring value. But the challenge here is that stochastic programming is not commonly used in practice, and I will talk about why. I'll talk more specifically about why, but the reason is really these solutions are very difficult to interpret. And these solutions are difficult to interpret because it doesn't, you have to think more about it because you have to think in terms of probabilities and scenarios, right? You have to think also about not just that you have different scenarios, but also that given different scenarios, you can make different reactive decisions or recourse decisions. So that makes it very hard to think about, even if you're very familiar with the application. And if I give you a deterministic formulation, you will be able to perfectly explain the solution. So that kind of inspired this work essentially. So where we see that where we kind of assume that this is for a user who understands the deterministic model. So if it's just a deterministic model, this is simple enough for that domain expert to understand these solutions. But really, the main complexity comes from the fact that you have many scenarios and you have many recourse variables associated with these scenarios, and these recourse variables can change depending on the scenario. And so, really, that is not very interpretable. But it's the deterministic formulation, on the other hand, is very interpretable. So I mean, we may want to get something in between. Maybe if we can get a alternative formulation, kind of a surrogate model that has fewer recourse variables and fewer scenarios, then that will be more interpretable. So then that will enhance kind of the explainability of the solution. And that's really the main idea here. And that's really addressing these cases where you have a lot of scenarios and a lot of recourse variables. And this is also inspired by, again, explainable AI, right? Because in explainable AI, one key way to do it is to reduce the complexity of your model. So essentially, if you have a neural network that's very complex, that's kind of black box, very difficult to explain or interpret, if you can replace this with something simpler, if you go further to the right, to the left, the simpler the get and the more interpretable the get. If you can replace it with a linear regression, that's perfect. And it's very easy to explain. Decision trees are a bit more complex, but still fairly interpretable, explainable, and then you go up in complexity, right? So this inspired kind of our approach to say essentially explainability or enhancing explainability through complexity reduction. And the complexity reduction in our case comes from reducing the number of recourse variables and reducing the number of scenarios. All right, so now let me get into what we develop here. So we focus on two-stage linear stochastic programs. So essentially everything is linear, continuous variables, and we have two stages. So here my X denote the first stage, or also called here and now decisions. The Y are my second stage, or wait and see decision here. This is just a general formulation. These are my costs. These are my constraints. Now you can see I have a set of constraints that only apply to X, and then I have a set of constraints that are for each scenario that apply to both, that involve both X and my recourse variables Y. And the goal is to improve the interpretability of not the whole model, but the optimal solution. So the setting for us is I solve this presumably complex stochastic optimization problem, and then I get an optimal solution. And now I want to be able to better interpret this optimal solution. So I want to reduce the complexity around that solution, but not for like the entire input space for my model. So that's important to know. That's kind of distinction between this and some other methods that are focused on explaining kind of the whole model. So really the idea is you start with a large scale stochastic program. What you want to do is you get that optimal solution. You want to eliminate redundant scenarios. So scenarios that actually don't need to get to your solution. And then you get a reduced stochastic program. And then you could also identify what we call principal recourse variables. So recourse variables that are really important, that contribute to your optimal solution. Whereas there may also be variables that you define as recourse variables in your model, but then you don't actually need them as recourse variables, which means you can actually just fix them to the same values for all scenarios. And if you can do that, you say identify these recourse variables, then you are left with a fewer number of recourse variables that you need to interpret, that you need to deal with. So that again also gives a reduced stochastic program that is more easily explainable. And the idea here is really so we really do this. We take this route. We eliminate redundant scenarios. Then we remove recourse variables, and then we'll get to this reduced stochastic program. And we do it such that the reduced stochastic program has the same or similar objective value as the original model, and it has the same first stage decisions as the original model. Because only then, if they are in a way equivalent, you can use that to explain the original model, right? Otherwise, you're ending up with something maybe completely different. So let me start with a recourse reduction that gives an idea of what we're doing. So we want to generate a reduced stochastic programming model with fewer recourse variables. So this turns out to be a bi-level optimization problem. So we have an upper level and lower level. So in the upper level, what we try to do is this Z star here is the optimal objective function value that we get from solving the original stochastic program. And so what we want to do is given a K, so K is the number of recourse variables that I want to retain. Given that, I want to find the recourse variables that I want to keep as recourse variables, such that I get an objective function value that's the same as the original objective function value, right? So essentially, I want to minimize the difference between these two. I want to ensure that the first stage decisions are the same. So the first stage decisions X for my reduced model should be the same as the optimal first stage decisions for my original model. This is a binary variable that indicates whether a variable is a recourse variable or not. And then this summation of them equals K, saying, okay, this is the desired number of recourse variables. Please only give me K recourse variables that makes this work. Okay, so this is what I want. And then at the lower level, essentially what it means is I need this ZK here, right? I need this ZK here to be the optimal value of my reduced model. So that's what this lower level is. This lower level is essentially my original stochastic program, but with additional constraints. Here are non-anticipability constraints. So essentially here I treat all my recourse variables as potential recourse variables, and they're no longer recourse variables if they're all the same for all the different scenarios. And essentially they become first stage variables effectively. So then what you see here is if my VR is 1, that means they can be different across different scenarios. In that case, they are recourse variables. But if VR is 0, then these constraints, or what we call non-anticipated constraints, they force them to be the same. In that case, they are actually first stage variables, where they're effectively not recourse variables, right? So then to this problem, ZK is the optimal value, and that gives me the kind of the full recourse reduction formulation. This, of course, is the bi-level optimization problem. For smaller instances, okay. For larger ones, this can be fairly difficult to solve, because once you do the single level formulation, it gives rise to nonlinearities and so on. So it can be a bit difficult to solve. And so what we came up with is it's a fairly simple heuristic solution approach to this problem. And what we do is the main complexity actually comes from this constraint here, saying that the first stage decisions have to be the same. If we remove this one, what happens is this bi-level optimization problem can actually be formulated as a simple single level optimization problem. And the main insight is here, if you look at the structure, this ZK here, this is essentially the objective function of my inner optimization problem. But this is also the objective function of my outer optimization problem, or my upper level optimization problem, because this Z star here is just a constant, right? So then once these are gone, I no longer have really first stage variables or these constraints on the upper level variables here. So then I can collapse them just into one single level optimization problem. And you can prove that this is true. So essentially, this is the resulting problem that you need to solve. Of course, this is a relaxation. It gives you a lower bound. And once you have the lower bound, what you can do is you can get these V's, you fix them, you put back the constraints on X. And again, that resulting problem, where we call a verification problem, you essentially verify the V solution. That again is a simple single level optimization problem. So we're getting approximate solution. Of course, this is a heuristic. We're getting approximate solution by solving two simple single level optimization problems rather than one difficult bi-level optimization problem. Okay, let me just put this to practice. So we are looking at the large supply chain planning problem. So this has the same structure as the simple one that I showed you with 2 plants and 3 customers, but this now has 10 plants and 15 customers. Assume again, product demands are uncertain. The first stage decisions are production at each plant, and then recourse decisions are my transportation and purchase decisions. And so if you look at this problem, this has 165 recourse variables. If you count the transportation links as well as how much you can, as well the purchasing, external purchasing variables. So then we apply the recourse reduction on this. So what you see here is we vary the number of recourse variables. Of course, the more recourse variables I have, the closer I should come to my original formulation. So then the closer I should get in terms of my objective function value. So what you see here is I'm minimizing, right? So this dashed line here at the bottom, this is the optimal value of my original stochastic program. And then as I increase the number of recourse variables that I include, I come down in the objective function value of my reduced stochastic program. And then what you see here in blue, this is the lower bounding problem that I talked about. Of course, what you really the really upper bound, you're looking at the upper bound. These are the green ones. It fluctuates a little bit at the beginning, but it converges toward the end. So that maybe 22, 23 recourse variables, you actually get to provably the same optimal value as the original stochastic program, which means now you do have a reduced stochastic program with only, let's say, 23 recourse variables that give you the same optimal solution as your original problem. And so this is where you see that. And then I think actually in this case, I think it turned out 18 recourse variables was enough, but it doesn't matter. It can be 20, 22, 23. So a significant reduction in the number of recourse variables, then I'll give you a reduced model that gives you the same optimal solution. So now you can see these links are now the recourse variable instead of all of them. And then if you just analyze these decisions, so these are my first stage decisions now. My first stage decisions now don't only include production variables, but also transportation, because some of these transportation variables have become first stage decisions effectively rather than recourse variables. So now you can see these kind of clusters that will always remain. And this one actually doesn't produce anything, the plant A. And then if you apply it to a certain scenario, this is one specific scenario. This is what remains from your first stage decisions. And then you only have a few links that are added in your recourse decisions. And that's where the goal comes in, where we think if you achieve something like this should at least, compared to the original problem with a full set of recourse variables, should be much easier to interpret than the original problem. Especially now, I think this information here is useful because that also makes sense, right? Saying, oh, I actually don't have to. It's also more implementable because for a user saying, oh, these decisions I don't actually have to worry about them. They will stay the same. I only need to analyze and see if these decisions make sense in the individual scenarios, and that will reduce the complexity a lot for a user. The second part is on scenario reduction. I'm looking at the time here. I think I should be okay. So the second is about scenario reduction. If we talk about scenario reduction in the context of stochastic programming, that typically means we want to reduce the number of scenarios to reduce computational complexity. So it's usually a pre-processing step. But what we are talking about here is a post-processing step. So we solved the optimization, the stochastic programming problem, and now we want to apply the scenario reduction to better understand the solution. And here, the conventional scenario reduction usually does it based on the parameter values, so that the ones that are similar will be grouped into a one scenario. Where what we do now is we group them or cluster them in terms of the recourse variables, because we're more interested in which scenarios give the similar decisions and not similar parameter values. And so in this case, what we do is we have that the solution. We do a simple k-means clustering based on the recourse decisions, and then after that, we can also, once we have clustered them into different clusters, we can also try to get a representative scenario for each cluster. Again, giving you a reduced model that has fewer scenarios that potentially is also easier to understand. So the application that we look at here is as an electricity procurement problem. This is actually inspired from work that I've done in my PhD, and I can talk a bit more about why we chose this later on. So this is a plant that produces a certain chemical product, but it uses a lot of electricity. So what they have to think about is where to procure that electricity. They can procure it from contracts, longer term contracts, and or they can procure it from the spot market. The advantage of long-term contracts is the price is certain. You know what the price is going to be. But typically that price is on average a little bit higher than what you get in the spot market, because that's what you're getting for that certainty that you get from contracts. Whereas if you purchase from stock market, you don't know what the price is going to be for the next day. So there's uncertainty in that. So you first need to decide how much to purchase from the power contract. Then you fix that. And then after, because they're longer term, and after that in the day-to-day business, then you can see, okay, what are the spot market prices today? And then based on that, you can further purchase from the spot market if needed. If you're actually consuming more electricity than what your contract can give you, then you need to purchase from the spot market. And so so essentially each scenario corresponds to a profile of spot market price, and we do it for 24 hours. And so if you want to we looked at 40 scenarios, and if you want to cluster them based on essentially how similar these profiles are based on that realization of that uncertainty, then for example you cluster these two scenarios. And now let's take a look at once you solve the stochastic programming problem, what are the decisions you make in these two scenarios? They are fairly similar if you look at, so they're, especially for the later half of the day, they're the same. But for the first half of the day, there are actually differences in the solutions. And especially there are differences where in one scenario you actually shut down the plan, and the other one you actually you ramp up the plan, right? So they're actually quite different. Although if you look at these price profiles, they're very similar. Now, if we do the clustering based on the recourse decisions, then you can see we now cluster two different scenarios, and the decisions are matched perfectly, but the scenarios actually don't look very similar. Okay, but although the scenarios, in terms of magnitude, they don't look very similar, what you notice is that the trends are similar. So when the trend, meaning in one scenario the price goes up, at the same time in the other scenario the price also goes up. When it goes down, and in the other case it also goes down. And especially this is this one region where one scenario the price goes down, the other goes up. But in general, the insight from here is the trend in the price profile tends to matter more for your decisions than the magnitude. And then if you analyze this further, so we looked at this, right? So this seems to counter kind of the insight that or the conclusion that we just made. But if you look at what happens here, is that we don't actually purchase anything from the spot market in those time periods. And that's because in the later half of the day, we actually purchase everything from the contract. And so this uncertainty actually doesn't matter. If you just look at the first half, then the trend align very well, which is why the decisions are the same. And this is and again, so this is just saying spot market price trend doesn't really matter for the second half of the day. And this is if you look at other clusterings, if you go into, so this was, if we just I want to cluster the two most similar ones, and then if you keep on going and to say, okay, I want to cluster more scenarios, you see similar trends. But of course, the more scenarios you want to cluster into one cluster, the more dissimilarities you will see in this. This is just what this slide shows. Let me quickly finish up with the last few slides here. So then this is further validated by looking at the correlation coefficient. If you look at the solutions we get from the scenarios that we cluster into same cluster, if you look at the correlation coefficient for all 24 hours, you can see some of them actually don't seem to be very similar. But if you only look at the first 12 hours, they are quite similar, which again validates what we saw. So this is just to demonstrate that with this kind of analysis, you can get insights that are very useful from that context. And it was especially useful, that the reason why we chose this example is because I was trying to solve essentially the same problem in one of my PhD projects. It took me months to figure out why I don't get a value stochastic solution that's essentially non-zero. And so essentially I solved my stochastic program, I solved my deterministic optimization problem. I never got really any benefit from solving the stochastic program. Although the scenarios look vastly different. It was because you needed to meet a certain demand within that time horizon. So really, it doesn't matter how high the price is, you always have to produce that amount. So then your operation just depends on when it goes up and when it goes down. You try to produce more when the price is low, when the price produce less when price is high. So really just depends on the trend. Then if you look at the trend of these different scenarios, they are actually very similar, which means that if you just take one scenario and then apply deterministic optimization, it will get you pretty much the same solution as if you did with stochastic program. And so if we did some analysis like this, then we probably could have figured out more quickly. And this is just from scenario reduction. If we also do that, we can say we have 5 clusters. We we generate one scenario for each one of them, and then we look at the reduced model. Again, you can see here you get the same, at least first stage decisions in the original and the reduced model. Okay, I just conclude with my final slide here. Key takeaways is that for this particular class of optimization problems, we propose scenario and recourse reduction methods to reduce the complexity, and by doing so, hopefully allowing the user to get more interpretable insights from the solutions. The decision focus scenario clustering were really based on the recourse variables. They uncover relationships between uncertain parameters and decisions that we otherwise maybe wouldn't have seen. And the recourse reduction can provide stochastic programming solution of the same quality, and then it improves explainability and implementability because there are fewer recourse variables you need to look at. Finally, this was work mainly done by my PhD student Tushar Radhi, so I want to recognize him here. And thank you very much for your attention. I'd be happy to take questions if we still have time.
Well, thank you, Professor Zhang. That was an excellent webinar. Just some of the latest things. We've heard so much about explainable AI, so it's great to see a webinar on explainable optimization and just how you take those results and make them accessible for people who need to understand it. We had a webinar poll. I'll just review some of the results. Many of you have already responded to this. In which sector do you primarily apply decision making, possibly under uncertainty? Academic research and industry are the 2 highest. Government had no responses for this one. What is your primary goal in attending this webinar? Learning about new methodologies was 71% of the responses. Seeking new solutions for current projects and general interest in the topic are also about 30% of those. Which aspect of explainable AI optimization do you find most challenging? I think the major one here is interpreting complex models. I think, from the modeling aspect, it looks like instead of like the objective function, the solution is like, hey, I have a very complex model. What are the weaknesses or the constraints that are holding me back? So interesting response there. How do you rate your organization's current capability in handling decision-making under uncertainty? It ranged from excellent to poor. And most replied fair, which is the second to the last. Only 4 out of 17, or about 25%, responded excellent. So it looks like a lot of work to be done to handle decision-making under uncertainty. And then what tools or methods do you currently use for optimization? Proprietary and open source platforms are the 2 highest ones. And then only 1 said in-house developed solutions. And then what do you see as the primary benefit of implementing explainable AI? And we had enhanced model performance was the highest, and then facilitating troubleshooting and debugging next. Improved stakeholder trust was 3rd, and then 0 results for better regulatory compliance. I'll go ahead and share those with the members of the webinar today. So let's go ahead and just, we have a little bit of time for questions now, and thanks for those responding to those poll questions. Let me just lead with one question here. Thanks for sharing the counterfactual and surrogate models. It looks like we've gone a long way since Lagrange multiplier and shadow prices. What can you say as well about mixed integer problems where you have discrete variables?
Yeah, so actually there is some work in the academic literature on sensitivity analysis for discrete or combinatorial problems as well. Of course, that's much more difficult than for continuous problems. So I think also in that sense, these new methods they they are in a sense from a conceptual standpoint agnostic of the class of optimization problems, right? They almost treat it as a black box, so they will be applicable to this. But if you want to go uh, if you want to go deeper into optimization theory, that then makes a difference if you want to do sensitivity analysis. But these counterfactual explanations, as well as the surrogate models, of course, the surrogate models, if you do it data driven way, it often does not matter. Although, of course, it comes with higher complexity if you want to do it on mixed integer problems.
Mhm.
I want to one remark maybe on that. I feel this field, explainable optimization, we've struggled with this a lot because the objective of explainable optimization is so vague and kind of subjective. So there's no like a mathematical definition of, okay, this is the goal for explainable optimization. So we have to think, kind of conceptualize for ourselves, like, okay, what actually help a user to do this? And that led us, surprising to us, we thought initially, okay, we would do some kind of theoretical work on more optimization theory similar to sensitivity analysis, but then we ended up doing still conceptual work on new methods, but then the aim is to, do something that makes it more explainable, but it wasn't like a very determined mathematical goal, right? Which makes this, I would say, less theory heavy, but very conceptual still.
Hmm. Let, let me just address maybe from the poll questions. Kind of surprising to me that more on the explainable models, do I have my model equations right? Um, and I wasn't expecting that from the poll results. But can you talk about that? Maybe some of the tools that are available. You mentioned there's the OptiChat. There's some other tools that are out there that are, really geared toward more of this explainable. You've got in AI, you've got the SHAP values and other things that, packages that are really around that, trying to explain AI results. What are the features that are most important? But what can you say about tools or methodologies that are out there to really help with seeing if you have the model formulation right, the equations and the
Yeah.
constraints?
Yeah, I think one great example for in the optimization literature is this uh, IAS. It's a method for determining. So if you have a model that's infeasible, it tries to determine which set of constraints make them infeasible. So that in a way is a nice tool for you to kind of debug your model to say, oh, okay, I expect something feasible, but it's not. So where are the potential constraints that contribute to this? So this is an existing method that's been around for a long time. But for example, OptiChat, what it does is it takes that method in the background and connects that to a user interface so that you as a user can query in natural language, and then it can give you maybe some insight on which constraints to look at. So there are and that's kind of, I feel, the opportunity from a research standpoint in explainable optimization versus explainable AI, because we focus on optimization models. And one key difference is that we actually know the constraint, we know the formulation. Not always, but presumably we know the formulation. So it's not completely black box. And what the part that we don't know is like, okay, why certain things are optimal. But we can leverage our knowledge about the constraints to help us better explain, so that maybe we don't have to rely on just purely black box kind of methods to do it. Um, and I feel that kind of relates a bit to what you're asking. So in terms of developing methods that actually scrutinize these different constraints that you're putting in.
Mhm. Let me just take another question here from Farheen. Can you please explain how can stochastic optimization be used to optimize? And then I'll just put in here my application. This one's the performance of pre-vaporization membrane reactor and ethanol water separation. So there might be an application of interest. Maybe somebody is more domain expert, as you mentioned. You got to be an optimization expert, but then a domain expert as well. So let's say somebody's coming at it from a domain expertise. What advice would you give to them to really start to use stochastic optimization?
I would say first it needs to be a first it needs to be an application where there's significant uncertainty, right? So if you're saying my application, let's take the membrane reactor. Once you put it in operation, there are significant, let's say, differences in the feed that it will have, in the feed composition, or significant differences in operating conditions. And I want to see, okay, can I design such a reactor that will operate under all these different conditions? So I think first there needs to be that problem, and then I think often in stochastic optimization you need to have a good way to solve the deterministic optimization problem first before you go into uncertainty. And I think also it doesn't, what I mean by this is I think people often get disappointed by stochastic optimization if they try to apply it to something where the uncertainty is actually not such that you will get a lot of value from stochastic programming. So I caution people also from getting too excited, because it really depends on your application. For some applications, the impact is really high. And for others, you may think it may help, but in the end, it doesn't. And I think that's where in the initial conversation, really that is important, that you discuss the type of uncertainty you have, the level of uncertainty you have, and then try to decide, okay, should I actually go with stochastic optimization, or can I actually just do a lot of it already with simpler deterministic optimization?
Fantastic. Well, that leads to the next question really nicely. Deterministic optimization, there are many solvers and platforms that are available to solve those, both open source and proprietary. What about solvers or platforms that integrate the possibility of incorporating these variables with uncertainty, such as normal distribution?
Yeah, I think there are quite a few packages doing that kind of modeling too. I mean, there are ones for stochastic programming. There are the ones for robust optimization. Pick your favorite kind of stochastic optimization method, and there will be some package out there that does this. And mostly is, for you to put your input, it generates, for example, scenarios, and then allows you to just simply put in the scenarios and solve the problem instead of you formulating it mathematically as a deterministic equivalent. So there are a lot of these tools, especially implemented like Python or Julia. That's fairly easy to use. I mean, I don't think listing there are quite a few. So if you just look for those, you will find some that meets your need. Yeah.
Okay. Well, fantastic. Hey, I
Hey,
think we're
John, can
about.
I ask a question?
Oh yeah, Michael, go ahead.
Professor, thanks for the very interesting talk and your succinct explanation of stochastic optimization, which has eluded me for a very long time. So in the beginning of your presentation, you said that when you talked about stochastic optimization, you said that you treat the model parameters as random variables, okay? And that, let's say, is the basis of the stochastic optimization, yeah, the C variable. So, and then you said a little bit about how you would optimize, let's say, an existing unit where you consider the design cost and the operating expenses. Oh, by the way, in your plots, you had the cost of electricity as $10 to $50 per kilowatt hour. I think you meant cents. I've never seen cost of electricity that high.
Maybe I double check on that.
Those are prices in Hawaii, I think.
Okay. So, for operations in the process industries, we're interested in optimization. And I would like your opinion on what is the difference between uncertainty and disturbance. Because in general, in the process industries, what creates the uncertainty is various disturbances, either weather-related or process-related. And that is the reason, actually, we have the basic process control system to handle those things. So do you see any difference between the concepts of uncertainty and disturbance?
So in my mind, uncertainty is maybe a broader term for where disturbance falls under, right? Where you can have uncertain parameters, but I think disturbances, they have more of this this nature of, okay, there is a general trend, but it's kind of perturbations around it. Whereas, you know, if you could talk about generally uncertainty, that doesn't necessarily need to be true, right? You could have scenarios that are completely different. And that's kind of what I maybe a little bit related to what I talked about before. You need to know kind of the nature of your uncertainty to determine what's the best method to deal with it. Because in process control, I mean, the way to deal with uncertainty process control is through feedback, right? I mean, you see now what's happening, and then your control system will react to that, and that's the way to handle disturbances. And I think for disturbances that are, you know, at that level, it's this is a very good approach, especially because you can be very fast in your response, right? And you could think about, okay, using something more sophisticated like stochastic programming, but then the downside, the trade-off maybe takes longer to compute, and then you're actually not updating your control inputs, you know, that frequently. So there's a trade-off there, and so it really matters how your uncertainty looks like. But to answer your question again, I think generally disturbance to me are also uncertainties, but they are uncertainties of a specific kind.
Okay, thank you.
Well, excellent. We're out of time. You know, I had a couple other questions that came in, but just in the interest of time, I think we need to wrap up. I'd recommend, if you'd like to, and also for those viewing this, if you'd like to post any questions on the YouTube video, just in the chat area, and we can continue this conversation there. But Professor Zhang, thank you so much for the webinar presentation, the great overview of the field, and the motivating examples and just discussion that I think a lot of people coming into this webinar were just looking for new tools, new ideas, and I think you've inspired all of us. So thank you for that.
Thank you very much. Thanks, everyone.